Hi, in this lecture we are going to be talking about the naive-Bayes machine learning algorithm. Naive-Bayes machine learning algorithm is based on the Bayes theorem in probability and statistics, and Bayes theorem is a subject in itself. There are like books written on Bayes theorem alone and how Bayesian theory can be applied to a lot of real world situations. But for this particular class, I'm trying to really simplify Bayes theorem to just get the gist of how this algorithm is supposed to work. So to begin with, let us start with some probability. So we start with something called a probability of an event A occurring, and any event. We call it probability of A, P of A, and that is usually between 0 to 1. When I say 0 to 1, it is usually between 0 to 100%. So let us start with something like we have the World Cup, soccer World Cup, and we have Argentina and Germany playing, and then you can say what is the probability of Argentina winning the World Cup. So the event A we are talking about is the probability of Argentina winning the World Cup. And that it may be something like 0.4 or 40% chance of Argentina winning the World Cup, for example. Now comes Bayes theorem. In Bayes theorem, we talk about what is called conditional probability. So what is conditional probability is that you talk about trying to predict an event A, given that event B has already occurred. So rather than just predicting event A all by itself, you have some prior knowledge of certain other things that have happened, and given that those things have happened, how does that change the probability of this event A? So again, going back to Argentina winning the World Cup, the probability of Argentina winning the World Cup is, let's say, 40% or 0.4. But suppose you know that Messi is not going to be playing in the game. So you have what is called a prior event that has already happened. Let's say Messi got injured and he is not playing in the World Cup. So what is the probability of Argentina winning the World Cup given that Messi is not playing? Now that will be a different probability, maybe 0.1 or 0.2, which is 10 or 20%. So that is what Bayes theorem is all about. It is trying to predict the probability of an event given that certain prior events have already occurred. So this is the formula for Bayes theorem, the probability of A given B. So what is A given B? Meaning the probability of an event A occurring given that B has already occurred. The probability of Argentina winning given that Messi is injured. So event B has already occurred, and you know that B has occurred, and based on that you're trying to predict A. So what happens is when you're trying to predict something, you start with some percentage, and then as you know more and more information about that something around that event, something has already happened, that changes the probability of that final event. So suppose again, if Argentina and Germany are playing the World Cup final, you start with the prediction that okay, Argentina wins. The probability of Argentina winning is 40%, and then during the match certain things happen. And then people do keep saying this when during a match, they immediately say that okay, the first team scoring a goal typically has a probability of winning the match that is 70%. So that is actually conditional probability. You start with the probability that both teams have an equal chance of winning the match, which is 50-50, but they also say if somebody scores the first goal, then their probability of winning goes up by X%. If somebody scored the first two goals, the probability changes like this. If somebody is leading at halftime, the probability changes like this. So all this is called conditional probabilities. You're trying to predict the probability of a future event given that something else has already occurred. Here is an example that suppose there are 100 patients and the probability of a patient having diabetes. In general, the overall probability is 0.2. Now, the probability of having a patient having diabetes, given that the patient's age is greater than 50, which is what we call the prior event the probability the prior event happening, and that is 0.4. So obviously when you know more about the patient, the probability of that patient having diabetes or not diabetes keep changing. So this is not just one event. You can start having many prior events, not just one. So a patient's age is greater than 50, you know something, okay, that changes the probability. What if that the patient's age is greater than 50 and weight is greater than 150 pounds? And what if you add a third condition that the person is a male? So as you keep knowing some prior information about the patient, or what we call here the prior events, it keeps changing the probability or the outcome that you are trying to predict. And this is what the gist of Bayes' theorem is all about. I'm just really simplified the whole Bayes' theorem world into just one slide. Now let's move on to naive Bayes. What is naive Bayes classification machine learning is all about? It is the application of the Bayes theorem to machine learning. So naive Bayes classification is the application of the Bayes theorem to machine learning to do some classification predictions. The target variable you are trying to predict in the classification becomes the event A. And every predictor that you're trying to use in the prediction becomes the events B1 to B1, so B1 to Bn. So that is how you map your predictors and targets to the naive Bayes classification. The target becomes event A, that is you're trying to predict, and all the predictors becomes prior events. So the values of the predictors are actually like the prior events. And you are trying to predict probability of event A occurring given that B1 to Bn has already occurred. So you have a customer coming into your store and you're trying to predict if the customer is going to buy your stuff, and you B1 to Bn are basically the prior probabilities you already know about the customer, like the customer's age, the customer's income, the customer's preferences and stuff like that. So for example, if you look at this table we created in the earlier example, age, BMI and diabetic. So the way you would state these are like the probability that is diabetic equal to Y given that the age is 24 and BMI is 22, and the probability that for the second record is again equal to Y given that age is 41 and BMI is 36. One thing you do in naive Bayes classification is, unlike other algorithms which just come out and say, okay, this particular record is A or B, or this particular record is yes or no, it simply gives you the probability that something is a yes and the probability that something is a no. So it gives you a value of, it actually tries to predict the probability for each of the possible outcomes for the target variables. The target variable is purely a yes or no. It gives you what is the probability that yes occurs and what is the probability that no occurs. If the target variable is something like high, medium, low, it gives you the probability for each of them, and then you basically go and pick whichever is the one with the highest probability is what I'm going to use for my prediction. So how does naive Bayes algorithm work? It basically builds this kind of a table, this kind of a probability table by reading through all the data it has, and it builds a probability table like this. So let me try to explain this table. So this table is built upon 3 columns. We are trying to predict the salary of a person. So salary is the target variable and salary is between less than 50 and greater than 50. You're just trying to predict, is this person's salary less than 50K or greater than 50K? And the predictors you are going to be using are age and gender. Now looking at the data, you are going to, looking at the training data set, you will build this table. And in this when you're building this table, how do you build this table? You first start finding out overall probabilities within the training data set. So you start with here, the training, which is the overall probability of the outcome. Less than 50 is 0.75, greater than 50 is 0.25. This is overall probability based on the training data set. Suppose that the training data set has 200 records, and this, when you say 0.75 is the probability of less than 50K, it means 150 records in there actually have salary less than 50K. Training data set, so you already know the outcome. This is the overall probability. Overall, how many people are less than 50K? How many people are greater than 50K? You do the same thing for age, every range in age here. So you see that in the training data set, if what is the probability that somebody's age is between 20 and 30, that comes up here, 0.24. Similarly, 30 to 40, 0.26. You do the same thing. So for every possible classification available in age, you find the overall probability. Similarly, for every possible classification of gender, which is male and female, you find the overall probability. Once you find the overall probability, you find what is called the joint probability between a predictor and the target variable. So what is the joint probability is what you see in these middle cells. So let us say take this 0.25. The 0.25 is the joint probability that a person's age is between 30 and 40 and that person's salary is less than 50k. So 0.25 is the probability that somebody's age is 30 to 40 and salary is 50k, less than 50k. So same way you build the joint probability for all these guys. So this middle two rows you see are the joint probabilities between the target and the predictors. So you find the overall probabilities and then you find the joint probabilities individually. All of them are probabilities. Simply take the number of records this conform to this condition divided by the total number of records. That's how you find probabilities. Pretty simple, straightforward. Total number of records in which this condition applies. So when I say 0.25 is what 0.25 is the probability for age and less than 50k. This basically take the number of records in which this applies divided by the total number of records. Pretty simple and straightforward. One thing you will notice is that the sum of these probabilities always comes out to 1. So the overall probability 0.75 to 0.25, the overall probability will always be 1. Same thing with gender, 0.33 plus 0.67 will be 1. The same thing applies for these rows too and these rows too. So all of them are going to be like, the total is going to be 1 because it's the total probability of all possible outcomes. Once you have this table built, it is pretty simple and straightforward for you to do any kind of prediction. And how do you do that prediction is, suppose when a new prediction is to be done, you apply the conditional probability formula we just talked about, which is probability of A given B is equal to the probability of B given A into something something. So we just talked about in the earlier slide. So suppose I want to predict if the salary of a person, what is the salary of the person, is it less than 50k or greater than 50k, given that I know that that particular person's age is equal to 25. So that means probability of salary less than 50k given age equal to 25. I try to predict both the probabilities, probability less than 50k and greater than 50k given that the age equal to 25, and I just borrow the information from this table, put them in, just apply. I'm just applying the formula. So what am I putting in the formula? I'm trying to put the overall probability that somebody's salary is less than 50k divided by the overall probability that somebody's age is 25. So I'm just borrowing them from 0.75 here and then 0.24 here. I'm just borrowing these values multiplied by the joint probability that somebody's salary is less than 50k and age equal to 25, and that is borrowed from this particular cell, and I just go ahead and compute the value. So I compute both the values and compare the values. Obviously 0.92 is higher than the value 0.08, so that means that we are predicting here that the person's salary is less than 50k if that person's age equal to 25. So this is how naive Bayes algorithm works. It just first builds this conditional probability table we saw, and then just applies this conditional probability table. So when you have new data, it goes and applies the tables, the numbers you found in the table, to the formula and comes up with the result. It finds an outcome for it finds a probability for each of the possible outcomes, and then you decide which ones you want to choose based on them. So let's go through some of the advantages of naive Bayes. It is simple and straightforward and fast again. It works well with noisy and missing data. It provides probability as a result, which sometimes may be pretty helpful because let's say I'm trying to predict yes or no. Sometimes yes is 0.9, the probability of yes is 0.9, and sometimes no is 0.2. Sometimes yes is just 0.55 and no is 0.45. So based on that, I can make some decisions. When naive Bayes is giving me a very high prediction that somebody's the outcomes probability is greater than 0.7, I can just go with it. But if naive Bayes is coming more closer towards a 50-50 kind of a split, then maybe I can use some additional algorithms to make more decisions. So I can make those kind of decisions based on the outcome of naive Bayes because I'm getting the probability for each of the possible outcomes. In other algorithms where it is just trying to predict only yes or no. I don't know how close yes and no's are, but in this case, I will know how close yes and no's are. So that is one of the advantages of naive Bayes. Shortcomings, again, it has limited accuracy. It expects the predictors to be independent, and this is an important one. The reason Bayes is the naive Bayes algorithm is called naive because it makes some naive assumptions, and that naive assumption is that the predictors are fully independent of each other. The assumption that the Bayes theorem makes is the prior events we talked about, the B1s to V1, each one of them are independent of each other. In other words, the B1 should not impact B2, B2 should not impact B3, which means one prior event should be independent of the other prior event, which means one should not influence the other occurring. So that is what one of the important things about the Bayes theorem is that the prior events are independent of each other. What I mean by independent of each other is that, let's suppose the one prior event is age and the other prior event is weight. The age should not in any way influence the weight. That's what it is trying to say. Suppose you have a third variable, something like their cholesterol levels. Now it may be possible that your weight has an impact on cholesterol levels. So the weight and cholesterol levels are not really independent. They have some amount of correlation coefficient. So when you say two variables are independent of each other, it means that their correlation coefficient is pretty low. That's what we are trying to say. The independent events or the prior event should not have any correlation between them. That is what we call by independent, and naive Bayes makes that independence assumptions. So when variables are really independent of each other, the naive Bayes will work very well, but if they have internal dependencies, it is not going to work that well, and that is what we try to mean by this statement. It is again not good with a large number of numeric predictors. If you have numeric predictors, you have to use binning. So naive Bayes only works well with classes for predictor variables. So when there are numeric variables, you have to convert them into bins like we did for age just now. You have to convert, if you have a continuous variable like age, you convert them into age ranges, 20 to 30, 30 to 40. So you have to bin them into these and bin them into classification in this case. Where is naive Bayes used? It is typically used in medical diagnosis because you want to predict if some person has a disease or doesn't have a disease. So this is where knowing both the probabilities of both the outcomes is good, because if you're trying to predict a patient has disease or not, if the probability of no is very high, then you ignore the patient. If the probability of yes and no are pretty close to each other, then maybe you subject the patient to further test or something like that to do more medical analysis. So that way, naive Bayes is pretty useful. It is used in spam filtering, trying to figure out if a particular email is spam or ham. Again, in this case, what is very useful is this percentages. So if the spam filter comes up and says that the probability that this email is a spam is very high, typically that process will kill that particular email and not send it to the receiver at all. But if say it comes out with a spam prediction that it has a 60% chance that this is a spam, then you might send the email to the person, but there may be a note that like says this particular email might be a spam. So that is why in the email title you will see that there is the marking which says possibly a spam. It puts a question mark. So those kind of decisions are made on the probability values that are returned by the spam filtering algorithms, and they are using naive Bayes to do that. It is used for document classification, trying to classify, let's say, news articles into whether they are articles related to sports or politics or something like that. Again, it comes up with those probability for each of the various classifications available. Again, pretty useful. So that's all. And then finally, sports predictions, as I talked about, trying to predict the outcome of a game based on certain events occurring or already occurred. And this is again where naive Bayes is useful. So probability that somebody will win a game given that they scored the first goal, or given that they are leading in halftime. All of that is sports predictions. Again, naive Bayes comes into play in these cases. Thank you.